So, here's a thought experiment for you. Picture this. You're floating thousands of feet above, suspended in a wicker basket beneath a colossal, vibrant balloon. The world below is a quiet, beautiful patchwork quilt. The air is still, the silence is profound. Then someone decides to jump out. A skydiver takes a leap of faith into the vast emptiness. What happens next? Does the balloon just keep floating peacefully, or does it shoot upwards like a released cork? Or does something far more unexpected and more dangerous occur? We assume less weight means more lift, but as Mythbusters taught us, intuition can fail. The universe has rules that don't always match our gut. Ballooning's serene grace meets skydiving's extreme thrill, a perfect platform without airplane noise, or so it seems. The interaction between the jumper's exit and balloon stability is a delicate, perilous dance. We'll break it down piece by piece. Before the big reveal, we need a foundation: buoyancy, gravity, air pressure, and temperature. Understand them, and the mystery unlocks. Let's get started. First things first, how do these magnificent contraptions get off the ground? A hot air balloon is a beautifully simple machine. A giant bag called the envelope, a basket for people, and a burner. That's it. But the magic is in the principle: hot air rises. You see it every day. Steam lifting, heat shimmering. The balloon supersizes that idea. The burner heats the air, molecules spread out. Less dense air inside becomes lighter than the cool air outside. Like a log in water, displaced fluid pushes up. That upward push, buoyancy, lifts the balloon. Gravity pulls down, buoyancy pushes up. The pilot balances them into neutral buoyancy across envelope, basket, fuel, and people. Short bursts climb, cooling descends. It's a delicate dance with physics, floating like a submarine in an ocean of air. The balloon and basket act as one suspended system. Every piece adds to total weight. And this is where our mystery begins. What happens when you remove a big chunk of that weight suddenly and violently? That's the trigger for everything that follows. Our balloon floats in perfect balance. Now for the dramatic part, the skydiver jumps. A 200-pound jumper seems small against thousands, but the key is speed. Weight vanishes instantly, so the balloon gains excess lift and starts to rise. Jumping isn't gentle. You push off the basket, imparting a sharp downward jolt just before the weight is gone. Two things happen almost simultaneously. The system gets lighter, primed to ascend, and the basket receives a downward shove. The envelope is a massive, flexible bag. The basket is a heavy pendulum. They can move independently, and that disconnect is where surprises begin. The sudden weight change plus the push sets off a chain reaction that can change everything in an instant. To really get it, bring it down to water. You're in a small canoe with a friend. The boat floats peacefully. Your friend stands and jumps out. The boat doesn't just float higher, it lurches violently, rocks, tips, maybe even takes on water. To leap, they push off the boat. For every action, an equal and opposite reaction. The boat gets shoved sideways and down. Same in the balloon, the skydiver pushes, the basket gets a shove. That's the first destabilizing piece. Then after the shove, the system is lighter. Lurch first, then sudden surge in buoyancy. A recipe for instability. Boats can slosh to bleed energy. Balloons are tied to a giant, non-rigid bag of hot air. The energy release can be far more dramatic and dangerous. The jumper leaves, the balloon gets lighter, so why would it fall? The basket is heavy with inertia. The envelope is a giant floppy bag with drag. They don't move as one solid unit. The push accelerates the basket downward for a split second. The envelope lags. Cables can go slack. The basket briefly enters freefall. As the basket falls, it drags the envelope's bottom down, deforming its shape, squashing volume, even folding the mouth inward. Lift depends on displacing a big volume. Deformation reduces volume and spills hot air. The whole system starts falling together. For those terrifying seconds, the basket is disconnected from lift. The stable giant can turn into a falling object. Lift comes from the big envelope volume above. Weight concentrates below. Basket, fuel, pilot. A low center of gravity keeps stability. Jumps rarely come from the exact center. Pushing off the edge introduces torque, not just down, but a tip to the side. That tipping can worsen the falling sensation, unbalance others, and yank one side of the envelope more than the other. The jump, the downward push, slack cables, basket falling, envelope deforming, hot air spilling. It's called the parachute effect, or balloon collapse. The falling basket can pull the top down through the collapsing fabric, turning the balloon into a useless streamer. Once it starts, it's brutally hard to stop. There's a subtler effect. As the basket drops and the balloon moves downward, a low-pressure zone forms at the crown, like airflow over a wing. Lower pressure cools the gas, adiabatic expansion. The crown cools fast, the opposite of what you need for lift. Hot air spills from the mouth, the top cools, buoyancy drops, descent speeds up, pressure drops more, a vicious, self-reinforcing loop. A small disturbance can escalate into catastrophic failure when balance is upset. It's a dramatic reminder, in this system balance is everything. People skydive from balloons safely. Certified pilots are masters of applied physics. They prepare the balloon for the event. Primary technique: put the balloon into a controlled ascent before exit. Sustained burn to create strong upward momentum at jump moment. Upward velocity keeps suspension lines taut. The basket may jolt, but it doesn't freefall. Lift stays connected. Modified balloons with more rigid throats resist mouth collapse. Pilots run meticulous weight and balance for each jumper. Sometimes jumpers exit simultaneously on opposite sides to cancel torque. Choreography matters. It's not magic, it's science and great piloting, turning risk into a controlled, thrilling experience. Under the wrong conditions, a jump can trigger a perfect storm. Sudden weight loss plus a downward shove can drop the basket, slack the lines, collapse the envelope, and spill hot air. We saw how balloons float in balance, used a boat to grasp the jolt, explored freefall moments and deformation, and uncovered crown cooling that accelerates the fall. But knowledge, equipment, and an experienced pilot change everything. A controlled ascent buffers the system and keeps lift connected. So, the answer is yes, but yes, it's dangerous. And yes, with preparation and respect for physics, it can be done safely. Understanding the science doesn't kill the magic. It makes it more amazing.